How's it going? Welcome to the office hours of Friday, November 5th for heap stuff. It's gonna be great. Where's my? There it is. Let's give a chance for a couple people to cycle in. There was a bit of scheduling confusion. At one point I was running late. I delayed and then I unran late. So we might have other people jumping in at 3:45. All right. Anyways, the way that we're going to do this, I guess people will trickle in, possibly. We got a couple of people here, and then otherwise, if you have questions, just ask, and we'll go through concepts. Otherwise, you'll just sit here watching me type, and I'm actually right now putting together a questionnaire, like feedback form. We'll be asking, okay, perfect. Can we see 6? And puts flag. All right, we have questions. So there goes my time to make the feedback form for pwn.college. Okay, that's all right. Let's dive in and get everything set up. All right, let's clear out that. Perfect. Okay, so if we go to the dojo, I left to go do other assignments the past few days and only just finished 5. Awesome. So let's, someone has a question about puts flags. Let's launch it up. Level 5, 0 is fine. Okay, let's do practice in 5-0. We will SCP it over as usual. I need to synchronize these stupid keys. Or what would be really cool is if we could put multiple public keys in here. All right, because right now every time I switch between my laptop and my desktop, I have to redo the keys. Okay, cool. Anyway, so we redid the keys. We spun up the challenge. Let's grab it. Boom. Okay. What am I doing? Let's run it and see what we've got. At this point, we're well familiar with the playground, right? So here we can do malloc, free, puts, read flag, puts flag, and quit. And we can make manage up to 16 allocations. So what does this get for us? Well, of course, we can malloc. It'll ask us the index. So this is 0 through 16. What happens if we do 100? It quits, as it should. All right. That was a test. We do malloc, index 0, size 16. Awesome. Here is our allocation. We have the result is this. And then we can, of course, do puts. It asks the index 0. There's nothing there. We can do puts flag. This is interesting. A read flag, presumably, like earlier levels, will allocate something for us and read the flag. That's awesome. So let's try to do what we did before, which is in the last extended Q&A, we did a little thing where we would allocate in index 0 something of 848 bytes, and of course you can put everything on one line. Scanf just separates on spaces, and this is all, as we saw reversing previous playgrounds, this all uses scanf. All right, so we malloc into index 0 something of 848 bytes. Then we can free index 0. And let's zoom out a little bit so we can read that. Okay, so here's our the state of our Tcache now. In bin 52, we have the thing we just freed. And then we can do read flag. All right, it allocates the thing we just freed because that's how Tcache works. It reads the flag into it, and we can do puts 0, and we get nothing. So what the hell, right? What happens if we do puts flag? We get that we are not authorized to put the flag. Okay, now we need to figure out what the hell is going on inside this binary by reverse engineering it, because we have a loss. This, we got a overlapping allocation, right? Allocation 0 is pointing to it. So what is going on? Let's take a look. All right, here is the little X server that I am running IDA in. Okay, IDA crashed. That's great. Let's just restart it just to be on the safe side. Tools, IDA, free, IDA, challenges, baby heap, level 5. Okay, it's not going to leave me alone about IDA crashing. That's okay. All right, here we go. We got this little playground we have. Again, this is IDA failing to decompile a switch statement in a loop. So we have to kind of decompile it in our heads. This is what runs every time. It'll print the Tcache, and it'll ask us for what we want to do. This is if we choose malloc. And here's that allocation index that we triggered already once. And then it does the malloc, and all is good. This is if we choose free. This is if we choose puts. And this looks normal as well. It just puts out the pointer. This is if we do read flag. What will it do? It'll go once. So starting from 0 less than or equal to 0. It'll malloc a buffer for us, and it'll read the flag into it. Okay, all normal. Puts flag. If this, so okay, hold on. This is a, okay. So I don't know why size 4, why IDA thinks this is size 4, but this is our flag buffer, right? Flag buffer. Let's just do flag buff. One word, because we're cool like that. All right, flag buff. This is interesting. Flag buff seems to be a structure because we are dereferencing it and seeking partway into it, even though we malloc the whole thing here. So it's a structure of 250 bytes. All right. Convert to struct. I couldn't create new struct type. There we go. Okay. So flag buff has a keyword. Oh yeah, and IDA automatically figured it out from, wow, this is impressive. IDA didn't used to have this capability. So it analyzed, wow, you can't, well, you might have a hard time reading this, but IDA analyzed that there's some keyword over here And then there's another 8 bytes, and then there is a gap. So here we go. It recognized that there is a authorized flag, it looks like. Let's just call it auth flag. Awesome. And then here is where it reads the contents of the flag to. Okay? So, nice and simple. What we actually allocated isn't just a flag buffer. We allocated enough space for a structure. And this is a very standard, what's it called? A pattern that you might see, right? You allocate the space that's big enough for a structure, even though that structure has multiple components, multiple members, right? And that's what we did. Allocate our buffer. Boom. Boom. Okay, so the unfortunate thing is that this gets zeroed out on allocation, the auth flag, and what it needs to be is non-zero. So my question to you, and I'm going to give you this hint and let you go and go on from there, is how do we read the flag, right? Obviously, that's the obvious question. Sorry, I had a better question, but I'll lead up to it. One is, obvious solution is puts. Unfortunately, puts will print things out starting from the very beginning, right? This is our allocations buffer. And it'll print out the allocations buffer from the very beginning. The way that we overlapped addresses that we overlapped our allocations, if we go and look here, the way we did this ended up with puts will start printing from the very beginning of that flag buffer because it's just pointing directly to this, right? Let me see what's going on. Marina, привет.
Привет, папа.
Shoes?
Пошли.
Давай.
Один. Пошли.
Давай.
быстрее.
Давай, хат. Быстрый хат. Ой, скажи. Привет, студенты. Привет, студенты. Потом сядь. Потом сядь. Окей. Окей, давай. All right, I'm back. That was a baby yawn intrusion. So, puts is no good for us because it'll puts things out, but it starts them from the very beginning, and the very beginning immediately prints a C string, which is a bunch of bytes ending with a null byte, and of course that null byte happens right away because when we allocated the flag, we nulled this out. Whereas read flag, unfortunately, because this is nulled out, or puts flag, refuses to put the flag for us. So we need to figure out a way using heap trickery to make this not null. Or if this was kind of one of the toddler challenges, so if, you know, control flow redirection, control flow hijacking was in scope, to jump directly to here with some crazy return override or whatever, but that's not the point of this challenge. The point of this challenge is to use heap trickery to either leak out the flag contents directly or set this to a non-zero value so that puts flag works. Sweet. That's where I'm gonna end it here. You have the tools to do it. Think about what happens to the values at those offsets in the allocation, like at the very beginning of the usable space of the allocation, when you do these various operations. For example, this is where the flag is read right now, starting from 0, right? Of course, this is null, and that's why you're having problems. Oh, shit. I wasn't on the terminal. This is where the flag got read into, or this got allocated, the flag got read into here, starting from here plus 16, right? As we saw in the buffer, in the structure. Whereas this is what's checked for whether or not you're allowed to read the flag. And you can make that non-zero. All right, that's number 5. Sorry, getting some caffeine. I slept for 12 hours last night after all the all-nighters. It was incredible, but now I feel like, hungover from the sleep. All right, let's check out number 6. I'll give you direction there, and then we'll move on to 7 and 8 if time permits. Let's take a look. All right, level 6. Hit the practice. All right, we're running. Brilliant. 6 and 7 are the same with one tiny change. In some sense, all of these challenges are the same with one tiny change, linking them together. But yeah. All right. Baby heap level 6. What do you have in the playground here? All right. We can manage up to 16 allocations, and there's a secret located at a known value. And in this known value, we could also reverse engineer the program to figure out where this known value is. So, if you can leak out the secret, we can redeem it for the flag. So what does this mean? Let's check out this send flag. So it asks us for the secret. And if the secret is apparently not correct, then it'll tell us to go away. All right. Otherwise, we have malloc free puts and scanf. Scanf's an interesting one. Let's see what that's like. So malloc. All right, we malloced it. We can put. Nothing there. Of course, what does scanf do? Scanf tells us, hey, where do you want to scanf to? And then it reads in what you want. Scanf now puts of 0 will give us that data back. Right? All right. And then, of course, free 0. And then we have our thing in Tcache. Now, the interesting thing, of course, what's the bug? It's not that malloc and free are buggy and shouldn't be used on their own. The bug is that we can still keep using the allocations that we are that we just freed. It's a use after free. But if we try to free it again, right? Double free, so you can do any of the operations again. So if you do malloc 016, free 0. What if we do scanf now? Let's do 0, and we give it x, y, z. Hey, look at what that is. X, y, z. We can overwrite parts of the metadata that is used by Tcache on this free chunk as the chunk is laying in Tcache. Tcache assumes that no one is going to mess with its metadata. Very few libraries assume people will mess with their metadata. And if someone messes with this metadata, crazy things happen. So I'll show you. Will I show you one example? I'm trying to think how close to the solution can I get without just walking you through the exact solution. Let's malloc into offset into index 10, something of size 1237. All right, this is now in allocation index 10. It's a here we read boom into it. So here's data is boom. Awesome. How am I gonna inject input into this now that I have it running? Okay, hold on. I'm gonna try something crazy. Will this work? Oh, we killed it. Oh, I see, it didn't work. Bummer. Huh. I wonder why that doesn't work. Okay, no, I think I understand why it doesn't work. That is just the... Yeah, okay, that's not gonna fly. Alright, what can we do with it? I bet... What if we... Sorry, I'm going off on a crazy tangent, but you know, sometimes you can't stop. We cat FDSA here, and then we cat into FDSA. Okay, and if we this works. This works. Okay. So now, can we redirect our own input? Yes. Okay. Crazy application of FIFOs. Okay. And you thought FIFOs were useless. Thought you'd never need them again. Okay. Hold on, actually. Oh, this is crazy. Okay. The right way to do this, what I'm trying to demonstrate, is in pwn.tools, but because I'm now on the kind of manic side of sleep deprivation, post-sleep undeprivation, we're gonna do this. All right, insane input to insane temp insane output, and we're going to obviously run this in the background, otherwise it's hopeless. Okay. No, it's dead. No. Okay. The subshell is still trying to open these. Okay. All right. We're fine for now. So let's attach ourselves to the output. Perfect. And now attach ourselves to the input. It works. Okay. All right. So this works. But now you can also malloc 016 to sane input. Oh, it works. Okay, so now we can interact with this programmatically. And things should fly. Now I wonder what happens if we close this FIFO. Can we close it? And no, it tells us goodbye. Okay, we can't close and reopen it. And cat dies as well. So let's do this. We will put that. Yeah, that doesn't have to be in this subshell. That's good. Okay. We're gonna okay. So we can only the output was kind of a a lie. Was it a lie? Okay, can we duplicate the output? We get every other line. Oh, that's great. But if we attach to output elsewhere, oh, that's awesome. Okay, so we can, as long as this stays around. What if this dies? Will this broken pipe? Okay, then it dies with the broken pipe. Okay. All right. Yes, I think everyone is correct that. Yeah. So both condensate. We were trying to figure out the laziest way to interactively pass in arbitrary hex bytes, but we have it now. I agree, Ethan, that Pwn tools and switching in and out of interactive mode is much saner. But now we have an insane solution, so we can use it. Don't do this at home. Use Pwn tools. This is a crazy, not smart solution. It's really irresponsible of me to show you the solution. But you know what? We'll just do it just this once. All right. So we created two FIFOs, an input and an output FIFO. We're going to cat out the output FIFO for now here, but the nice thing is we can switch it over at will to figure out data, and then we're going to boom, start interacting with the service. This is crazy. Okay. And the whole point of this was I want to show you that if you do a malloc 1337 in position 10. All right, so if you malloc 1337, this is now our allocation. If we, how do we get at that allocation, right? So let's say I want to, I put in this boom into there. I can, of course, print it out. But how do I get it without accessing allocation 10? How do I fool Tcache into giving it to me, or fool the heap into giving it to me? Well, what happens if we malloc something, all right, and then free it in allocation 0? Here we are. It goes into a Tcache bin, right? And Tcache bin 0 covers sizes 0 through 24. There's one thing now in this Tcache bin, and that's what we just freed. If we malloc 016, it comes back to us, right? That same address gets pulled out of the Tcache, and there's nothing left in the Tcache, right? Okay, that's fine. And that's kind of what we've been operating under so far. Now, what if we malloc a new thing into position 1? Okay, so now we have two allocations. This is an address no one's seen before because it just is new. The heap pulled it out of the wilderness, right? And if you free both of them, all right, so here is free 0. Of course, I put all this in, and then it gets processed one by one by scanf, by the challenge as it scanfs. So free 0, it freed allocation 0. This is the state of the Tcache. Free 1, it freed allocation 1. And now this is the state of the Tcache. In bin 0 are two things. All right. And what are those two things? Those two things are, the first thing we freed is all the way at the end of the Tcache. It had been at the head, right? So it was pointed to by the head. And then this was its metadata. Now, we freed the second guy, the thing that was stored in allocation 1, this address. When we freed that, it got put into the head, the beginning of that single linked list. Here it is. The entry that it represents in its next pointer was written the old head of the list. So it just got inserted into the beginning of a singly linked list. Nice and easy. Back to data structures and algorithms, right? That's like 2 something. CSE. What's data structures? Your data structures course? Anyways, it doesn't matter. Basically, it's a single linked list. CSE 310. Interesting. That's... Okay. Yeah. So CSE 310, single linked list. Boom. So you might potentially take 365 before 310. Is that possible? Or is that 365 is a later semester? Same semester. All right, well, interesting. Okay, anyways. Okay, CSE 205 maybe. Maybe you learned this in 205. A single linked list. Singly linked list. So this, the head of the list, the Tcache per thread struct, points to the latest allocation you freed, which points to the second latest, which point, and so on. And how does it know when it's done? When, you know, because now if we malloc something, boom, it pulls out this first guy, right? So now we only have the second one, which is the new head again. And then if we malloc it, boom, nothing in Tcache anymore, right? How does it know there's nothing in Tcache anymore? 2 ways. It used to just use this nil, the next pointer. And if there was a null pointer there, it would say, okay, that means we're done. Now it tracks the count. It no longer checks the value of this pointer. It just has a counter in the Tcache per thread struct that says how many entries there is. Why did they switch away from one to the other? Well, my best guess is that this is too easily overwritable by use after free vulnerabilities. Which brings us to, what if you free them again? All right, so we free 0, free 1. Now we have 2 things here. We have a this guy points next to this guy, right? And so when you do a malloc, first this one will be returned, this value will be stored into the head, as we saw up earlier, and then this guy will be returned, and then this will be put in the head. So 0, and then since count is 0, that Tcache is empty. All right. Now, okay, I just saw on Twitch, linked lists are in CSE 205. So you're all old hats at linked lists. That's great. All right, now we can scanf, and as you saw, we could scanf into next. We already did the scanf 0, 1 because you just recall that that pointer is not invalidated. It's not set to 0 or whatever in the binary after it's freed, so we can keep using it, right? Scanf 1, okay. And we do XYZ. Now what happened? Now we hijacked the whole freaking single linked list. We can't hijack the head. We don't have a write access to this the Tcache per thread struct, unfortunately. But we do have the right access to this metadata, and we replaced it with XYZ. Hold on, let me see what this phone call is. It's from a... Hello? Yes? All right, as expected, that was spam, but when you... The one of the most unexpected things about becoming a parent is that random phone calls could be like from daycare or something, right? So you can't just ignore unknown callers anymore. It's infuriating, and as a result, you end up answering a lot of spam calls. Anyways, okay, back to reality. So we can overwrite the next pointer and hijack Tcache, right? So then suddenly Tcache thinks, oh, okay. After we allocate this, the next allocation that's going to be returned is this 5A, 5.9, 5.8, which is wild, right? So we can control on allocation, right? Watch this, malloc. This is probably going to segfault. You malloc. Let's put it into position 3. Boom. So that was the head. Now the new head is here. Malloc position 4, 16. And we segfaulted. Because malloc returned this insane number, and then of course, even though count is 0, what it probably did was try to dereference this to get its next pointer. But of course, this is all unmapped. So, no good. All right, so what if we hijack it into mapped memory? So now we have to set up our entire insanity again, because now it's actually relevant. All right, here it is. No, wait. Yeah, it's fine, okay. Cat, insane output, cat into insane input. Okay. So, let's set that up again. We malloced into position 10, 1, 3, 3, 7. Then we scanf into position 10. Boom. Awesome. Let's test that. Okay. Then we malloc into position 0. And then malloc into position 1. Buffers of 16 bytes. Oh. Nice. Dralucardcula has a very nice way in Twitch to avoid this insanity that I'm doing. So you just do cat pipe, and then you pipe into the input of cat instead of, yeah, okay, that oh, I see. Because cat creates a pipe, not a and then you don't get a pointer into. Nice. Okay, it doesn't matter. We already did it. I mean, it does matter. It's great, but we did it this way. It's we'll suffer for now. All right. So we have our 2 allocations, and then of course we free them both. And so this is the address that used to be in 1, or that is still in allocation 1, but it's now freed address. This is an allocation 0, and then this entry points with its next pointer to this entry. And so now we can overwrite its next pointer, and we're going to overwrite it to this value, so we can read out our boom without being like allowed to read out our boom, you know? So what's this value? C08295. Awesome. So we're going to malloc. No, we're going to scanf. We're going to scanf into this allocation 1, which we just freed, but which you can still use, which will override this. And of course, as a reminder, if you did XYZ, here we go, we overrode it with XYZ. Last time, when we started mallocing, things crashed, so we just don't malloc yet. Let's fix it up. I'm going to do scanf1, and then we want to write this address. So let's do it. So we're going to echo that xc0 x82 x95 into insane input. Okay, let's see what happens. All right, scanf blah, and a bunch of printable stuff. Oh, I didn't do echo dash e. Okay, so but okay, we scanf some stuff. You see, we also overrode the key. The key doesn't matter. The key only is checked when things are freed. Anyways, let's scanf and do it properly. Scanf into 1, and then here dash echo dash e. All right. what's going on? Yeah. Scanf. Oh, no. Scanf. 1. What are we doing? Boom. Why doesn't it like it? Why am I still getting ASCII? Oh! No. Scanf 1 XYZ. Oh! I see. I I'm not overwriting this. So okay, we need to fix this. That's fine. Oh, what's going on? Scanf 1. Let's just give it a bunch of nulls. You know why this happened? This happened because we're insane. Okay, perfect. The key again doesn't matter. All right. Scanf 1. Boom. All right. Look what just happened. We just fooled Tcache into thinking that this is still the correct beginning of the list. And then we said, hey, don't worry about it. The next thing on the Tcache is our old allocation that we had allocated well before. That we had allocated right here. Right? And now, if we malloc things twice, if we malloc things once, it says, oh shit, your next allocation is here, no problem. It's just gonna read the next thing in the Tcache. When we malloc that again, we got it back. And here's our boom. All right, that's the technique you need. Now, I did walk you through the actual full solution, but that's the technique you need to do this. Now, again, I highly recommend using pwn tools instead of this absolute insanity that I did with either my insanity with FIFOs or Alucard's insanity with this. Very interesting question on Slack. Why the hell does puts only output 8 bytes? Now, in this case, we only had 4 bytes to output, but let's restart this. Okay, we're gonna malloc 10 1337. We're gonna scanf into it. Into 10 A B B B B B B B B C C C C C C C C. Okay, here it is. A lot of bytes. All right. If we malloc and set up our Tcache. All right. Here it is. We we need to get the. This is our address that we want. Okay. So let's redo this attack. We scanf into allocation 1, which was the last thing freed, which is now the head of the Tcache. And we're going to overwrite its, by scanfing it, of course, we scanf into its usable space. It's just functionality in the program that's buggy. It's not checking to make sure that allocation hadn't been allocated already, hadn't been freed previously. So we're going to overwrite starting from here, which now in the context of the program is metadata for Tcache. We're going to switch to this because we're insane. And then we're going to, oops. So XC0, X32, X4C. Boom. Okay. And suddenly we changed the Tcache. We redirected it, that single link list, to somewhere else. And that somewhere else was our allocation. We wrote AAA, first 8 bytes, BBBB, and then CCCC, right? And that, as a reminder, that's this. But now, if we malloc, do 2 mallocs, the second malloc is going to return this allocation. And notice something else really interesting is happening. This is a malloc 16, so the program thinks, no problem, I can put 16 bytes in here. That's true right now, but if the roles were reversed and we had gotten an allocation of size 16 returned, whereas the program expected to use more, then that could in turn lead to a heap overflow, for example. But right now, all it leads is us being able to put our data, except for we only get 8 bytes. Why? We only get 8 bytes because of something that Tcache does when returning, which is some kind of arbitrary thing that the developers decided on. Let's go into the source code. Let's go to malloc.h. And if we look at tcache get, this is the function, very simple, to retrieve data, to retrieve an allocation from tcache. And this is the index that it'll be retrieved from. It says, okay, grab that, the head of that linked list, update the head of the linked list to point to the next allocation, decrement the count, and null out the key. And the key is right here. So bytes 8 through 16, starting from 0. So the second keyword of each allocation is nulled out on malloc. You'll have to figure out how to get around that. If you need to read out or write in more than, or if you need to read out more than 8 bytes using this technique. All right. Let's see. This is, what level is this? 6? Yeah, this is level 6. And did we have other questions? There's a question about level 8. Level 7. So level 6 and 7 are the same with one tiny change. Now I'm curious what I put in level 7. Let's look at level 8 real quick. And then we'll probably call that a day. So just ran level 8. Let's SCP it. All right, let's see what we have in level 8. So in this challenge, there's a secret stored at a white space armored address. What does that mean? That means that part of the address has a white space character in it, a new line. Why is that a problem? That is a problem because when we do this scanf, when we, excuse me. When we do a scanf, if one of the values here is a white space, like a new line or something, scanf will stop reading, right? You are having trouble with this level because you are obsessed with precision. Perfectionism is often necessary in hacking in some way, right? Because there are cases where addresses need to line up perfectly. If you're returning to a buffer, you need to return to your code. But even there, perfectionism is not always necessary. Think of a NOP sled. A NOP sled allows you to return somewhere close to your buffer. or rather, somewhere close to your shellcode, partway into the buffer. Oftentimes, you need to know addresses before you can redirect control flow. But again, think of in baby ROP cases where, or in baby mem, cases where you didn't know the whole address, you just knew all but 3 of the nibbles, right? What did you do then? So think about in this context, what can you do if you can't perfectly overlap an allocation with the secret? So someone, 2 curbs is asked, can you use something other than scanf? Normally speaking, yes. In this case, the functionality of the challenge will only give you scanf. There's no other way to get input. This challenge never reads from standard input. I'm sure you could have a very convoluted, more complex than intended solution where you could make it read from standard input. But that's not, let's say that's not necessary in this case. You can solve this with scanf. All right, so to summarize today, we covered 5, 6, and 8. I know 8 was a bit vague, but it's very hard to give you hints that don't just give away the answer. So start with that. Think about, do you really need to perfectly overlap the allocation? The answer is no. Go from there. There are solutions to 8 where they are perfectly reliable. There are solutions to 8 which require a little bit of brute forcing. And that's fine. If you run your solve script 256 times before it works, who cares? Our infrastructure can take it. All right. We'll end it here for the day. Again, if you dropped in late, like I think there was some confusion if this was going to start at 3:30 or 3:45. If you dropped in late, of course, you can go to the VOD and rewind. That would be my suggestion. We covered level 5 right in the beginning. Awesome. Okay. Thank you for joining. Good luck. And see you on Tuesday or Connor will hold an office hours on Monday for the very last second questions. And I will see you, or we'll all see you on Tuesday for the launch of Baby Race. Hack hard.